Hello and welcome to episode 11 of our language design exercise. In the last episode, we wrote unit tests for our grammar. Now we want to go beyond the grammar and actually generate an abstract syntax tree. Because in compilers and interpreters, you, of course, use your grammar to check the syntax, but also create an abstract syntax tree for further processing, such as semantic analysis, optimization, and code generation. So previously, we got to the point where we asked OHM to parse our source code and return a match object. The match object has methods like whether it succeeded or failed. And if it failed, we can grab the failure message. I want to make a slight change here. What we want to do is take this match object, and if this match succeeds, we're going to take that match and pass it into an abstract syntax tree generation, AST, which VS Code is trying to force me to say assert, but I'll say AST. And I'm going to make this AST method, AST function, a function in a new file that we're going to be creating called ast.js. All right. So now what we're going to do is we're going to get the source code, we're going to parse it, and if the match succeeds, we're going to invoke the AST function on it. So we want to actually create a new file. Let's call it an src ast.js. Now it's created, and what's that going to look like? Well, this is going to be kind of busy because we need to use some functionality from OHM, which helps us walk the match object that it created. The match object is essentially a concrete syntax tree. Our AST function is going to look something like this. Let's export it as default function AST. We'll take in a match object. And what we're going to do with this match object is build an AST out of it. So in OHM, the way you would do that is to define your own operation that works on the match object. And I'm going to call this an AST builder, which we'll create above, pass the match object to it right now. And then the AST builder is just going to be some constant AST builder, which will be some object that we'll build after. Now, cool thing about OHM is that when you match a grammar, you have this match object and you can do anything you want with it. You don't have to make an abstract syntax tree. You could interpret it. You can use it for syntax highlighting. You can use it for anything. If you had a grammar for polynomials, you could evaluate or differentiate the polynomials. OHM, one of the strengths of OHM is that, once you match the grammar, you can do whatever you want with it. Whereas a lot of other tools like OHM, you have to put in the processing kind of mixed in with your grammar. So this idea of separating what they call semantic actions from the grammar is the strength of OHM. So given that, what this means is that if we have let's say a grammar object, some grammar object, we can build what's called a semantics object for it, semantics. And on that grammar, we can create any kind of operation we want. So I'm going to create an operation called AST. And the job of the AST operation is to construct an abstract syntax tree. So this is what it's going to look something like this right now. Okay. And so since our operation is called AST, once I invoke my AST builder on the match, I'm going to invoke the abstract syntax tree generator on the root of that tree. So this is how things are going to look for now. And where are we going to get this grammar from? Okay. Well, this grammar should actually be the same grammar that we generated from our parser in grammar.js. So I think I want to, we got to make some changes right here because I need to get this grammar used in the AST builder. But I don't really want to pass these objects around. So what I'm going to do is create a new file called core.js. And this is going to contain the actual, let's say, core elements and core entities of our of our what's going to be a compiler, basically. So let's take let's use this file to handle our grammar. Okay, so we're going to take our grammar and we're going to read it in from small.ohm like so, which means that we need to bring in fs, import fs from fs, and import ohm, whoops, ohm from ohm.js. And then we can get our grammar like this, and then our grammar can be exported from core, which means that in our AST library, again, what we're doing here is we're just modularizing our code so it all makes sense. If you had pre-planned all this, you probably would have created the core first, but it's more fun to build things this way. So in the AST, how are we gonna get this grammar? Well, turns out that this core module is going to get pretty big. I mean, okay. So for right now, no, I'm going to do it this way. Star as core from core.js, because it's going to get big pretty soon. So grammar is one of the things that I'm exporting from that. So I'll get it this way. There's going to be some more core operations that are done inside the builder. Since we've done that, our grammar should change just a little bit. Our grammar function, because we're now going to get all this good stuff right here from core. So we'll just import grammar, which is all I need from core.js. So what I'm doing here is our little grammar function is pretty nice and clean. I should be testing this as I go, right? It's probably not a bad idea. So rather than doing AST match right now, let's just see if we can. Let's go back to saying okay right here, just to make sure I didn't actually break anything. Okay, and we'll see if bad dot small up. We've got a problem here. Cannot find ast.js from small. Haven't used that yet. Okay, that's good. And let's try it from hello.small. Okay, everything looks good. All right, then I'll put this back to this AST function, which we don't yet have, but we will soon. Oh, here's the problem from earlier. I forgot the dot. Okay, that's what we want. Okay, so here's our main program, which is going to have parse, which it brings in from grammar.js. In grammar.js, here's parse. Parse uses the grammar that's defined in core, and inside of core, here's where we export the grammar. So you have things working. All right, now let's get into the good stuff here. If I'm trying to call the AST function right now, I don't really have much done right now. I mean, this is going to break because it says here there's some missing semantic actions, no default actions, and stuff like that. So here's how Ohm works. Ohm has what is called modular semantic actions, meaning that if you have a match object in Ohm, you can pass that along to some kind of something called the semantics object. So grammars can have semantic objects with different operations, one of which I'm going to call for now AST. And okay, so what do you do with an operation? Well, here's the thing. An operation on a semantics objects has one method for each of the grammar rules, more or less, one for each of the grammar rules. So if we look back at our small.ohm right here, we see that we have a program, statement, if statement, params. We need to write semantic actions for each one of these things. So as we traverse the matched concrete syntax tree, we can do something when we see a program, do something when we see a statement, an if statement, and so on. So we do things like this. You can see that a program has one element on the right-hand side, statement plus, which represents its body. So we create in here a method called program, which takes in a body object and does something with it. Okay. Now little, not very pretty right here. I mean, I want it to look more like this, but oh boy, what a mess. Okay. All right, here, let's just back up here because VS Code is trying to be helpful. It's never as helpful as you want it to be. I want program takes in a body to do something. And then before I save it, let's just leave it right here. I'm going to move this on the right-hand side. Split right. Okay. So I'm going to put my grammar over here. And we're going to see that for each grammar element over here, I'm going to make a method over here, or a method of my AST operation. So the first thing we had was program, has just one thing called body. So I'm just going to go there. The next thing is statement, but there's different forms of statement. Statement print comes next. Statement underscore print. And this has 3 elements: the print keyword, an expression, and a semicolon. Now, I don't really care about the print keyword, so I'm going to make an underscore there. And then I guess this could be an expression, and then a semicolon, which I really don't care about. So statement print's going to go here. The next one is statement vardec, statement underscore vardec. And the first thing that it has is the word let, which we don't care about. It has an identifier. And now it has an optional section here. When OHM sees something optional, what it's going to do is it's going to say, all right, rather than just one semicolon, it's going to give me back an array of semicolons. And the array will have either size 0 or size 1, because if I don't use this part in my program, then there will be no semicolon there. If I do use it, I'll have a semicolon. So OHM's way of saying you either have it or you don't is to give you an array of 0, 1 object. So I'm just going to say semis right here, semicolons, and then I'll have some types, and then I'll have equal. I do want types. I'm going to have the old equal sign, and I'm going to have an initializer for the expression, and then I'm going to have a semicolon, and then not going to do anything here. Next up is an assign statement. So statement assign, that's going to have an identifier, an equal symbol, an expression. Oh, I'm going to call this identifier. What can we call it? I mean, I guess, yeah. Well, you know what? It's a target, basically. Target equal sign source, and then semicolon, and do nothing here. All right. So got this here. Okay. So we're making some progress here now that there's room here. Now I can continue along doing everything I need to do here. Like what's next here after assignment? We have a while next. You can see the while is pretty short. Statement while. There's 3 parameters are going to come in here. There's going to be a while keyword, and there's going to be a test and a body. Those are the things that we're going to get next. Just before I go on, if statement right here, notice that there's just one thing called if statement. It's going to fall through here. So we don't need to handle this right here. We just kind of leave this alone. Break is next. Statement break, we'll handle the if statement later. Statement break has the break keyword, and it has the semicolon. And so things look pretty much like this. Now we're just going to continue in this fashion all the way down here. Each one of these things is going to need a method for it. And I'm going to get down to, well, let's get down to if statement. So I have these already made, so I'm going to add in a few more of these. Here's the try, and here's the if statement. You can see that the if statement will have the if keyword, that's this. The expression is a test. And then the first block right here, we'll call it the consequent, because if something, then something is a consequent. And then because this is in question mark there's 0 1 else's and 0 1 alternate, which we'll write as so. Okay. Next is params, and then param and args and block. And for parameters, you can see we don't really care about the parentheses. We do care about the parameters. I'm just going to continue along this route all the way down here till I get to the very last thing over here, which is the, well, I'm gonna go down to string literal. Okay, so all the way down to string literal. And then you see that we have char and space. When we make an abstract syntax tree, the individual characters are not going to be so important. So I'm just going to stop right here at strlit. I'm not going to go into char, and I'm certainly not going to go into space because spaces are actually skipped, but I'm going to kind of avoid char. Don't need to handle it for right now. I do have ID. I don't need to handle any one of these keywords. There's really nothing to do when we get there. Let's see about types. Type optional, type promise, type array, type dictionary. All are here as expected, right? Type has a type and then a question mark, which you don't care about, a type and then a caret for the promise. Int, float, bool, string, anything. I'm going to skip those, right? Well, actually, yeah, I mean, I don't really need to process them right now. So actually, how can I get away with like skipping these things? Like I'm skipping the print and the float and the bool, and I'm gonna skip all these things. What lets me do that is that in Ohm, if you ever have a category and it does not start with a capital letter, then it's what's called a terminal symbol. And terminals can be processed too. So I don't need a special rule for int or a special rule for float or a special rule for bool or anything like that, or even for while or print or let or anything like that. Because what I'm going to do is I'm going to let Ohm's rule terminal just handle them. So underscore terminal is a special rule in Ohm that will handle any terminal category that is a lexical rule, something that starts with a lowercase symbol, that is not otherwise handled in here. Okay. So things will look like so. And if I try to run my code right now, I get back undefined because I'm asking Ohm to say, generate the AST on the match, and the AST operation for my match, well, right now doesn't really do anything right now, right? If I wanted to, I could say return it begins or something like that. And if I now run this code, it'll say it begins. So what happens was I take in a program, in this case, hello.small, which just as a reminder looks like this. It just says print hello. What do we do? Well, first thing is I read the file into source code. So source code is the string print hello. I match it using my parse function. My parse function comes from the grammar, and it says match it against the grammar. The grammar comes from core, and that is the grammar that I read in from small.ohm. Okay, so far so good. Then, if the match succeeds, which it does, invoke the AST operation on it. This AST operation is defined in here. It takes the AST builder, applies that to the match, and then looks for the AST operation, which is here. And all the AST operation does, as soon as it sees a program, it just returns it begins, and therefore it begins is what is displayed from here. Okay, so that is almost hideously boring, but it's the start. It's the start we need. Now, what we really want to do, it's not just stop there. We need to emit an abstract syntax tree. When I see print hello, I want to emit an abstract syntax tree with, say, a program node at the top, and then a list of statements, the first of which is a print statement, which is going to say print out hello. So it's like I want here the following. I want to have a bunch of classes for my abstract syntax tree node. I want a program class. I want a print statement class. I want these. What else do I need? If I walk my way down here, I have a program. I have a print statement. I next have a variable declaration. Okay. Next, I have an assignment. Export class variable declaration. Export class assignment. Export class. What's next? While statement. I want to build for everything that's significant. It's going to have its own class. Okay, I'm going to define these in course. So program, print statement, variable declaration, assignment, while statement, break statement, function declaration, right? Export class, break statement. You write these for everything that matters. Function declaration, return statement, and on a try statement, if statement, parameters, and so on. I do want to say that when I get down to here, things get somewhat interesting. Actually, let me drop in just for completeness. Let's do the try statement, the if statement, and the parameters. Try statement, if statement. Actually, do I really need parameters? When I make a function declaration, I probably don't need a parameters object. It will suffice to just have an array of parameter objects. So I'm just going to go with parameter right here. Now, what about arguments? A list of expressions will be fine in my calls. What about a block? Do I really need a block object? Well, let's see. A program is a sequence of statements. Oh, sorry, no, we're talking about blocks here. While expression, here's a block, here's a block, here's a block, here's a block. I can just store an array of statements there. So I really don't actually need a block object. I can just store an array of statements. Be fine. Now, what about all these expressions? I have an unwrap expression, unwrap operator, an or, an and, less than or equal, less than equal, not equal. I got an additive operators, multiplicative. I have so many different kinds of binary operators. Do I need to have a class for every single one of these things? Actually, no. All I really need is I can just make a class called binary expression. And in a binary expression, it suffices to have just say an operator, a left argument, and a right. And I can just create my objects this way. We use this nice pattern for construction, like so. All right. So yeah, I'm just going to use binary expression. And while I have binary expression, I might as well have a unary expression for the unary operators. And then we'll just say op and operand. And we continue in this fashion. We would need an await expression, a empty optional, which you'll see here, a lookup expression, call expression, type conversions, parentheses, array literals, dictionary literals, optional types, promise types, array types, dictionary types, bindings, and so on. In fact, there's quite a lot of these. And for each one of them, we have to make a constructor for what's useful. For example, if I were to look up at the while statement, we saw that, okay, what are two things that a while statement has? It has a test and a body. So I would say something like constructor as a test and a body. And we would say object.assign this, and then test body. Okay. Now, if I were to just run through all of the different things that I need, paste them in, and you can guess I've already done that to keep the video a little bit shorter. Let me copy paste them in from above. Okay. I'm going to copy all these classes here. Let's see what we have. We say that a program has a body, a print statement has an argument, a variable declaration has an identifier, a type, and an initializer. An assignment, you assign to a target, a source. A while statement has a test in the body. A break statement has nothing of interest. It's just a break statement. Function declaration has a name, parameters, a return type, and a body. A return statement has an expression. A try statement has a main block, a timeout block, parameters for the catch, and a catch block. See the main block, the timeout block, the catch parameters, and the catch block. If statements have test, consequent, and alternate, this is the then part, this is the else part. Parameters have an ID and a type. Binary expressions, as I said before, as an operator left and a right. Unit expressions with an op and an operand. Await expressions. Here's the await. They have a timeout, and then they have an action. And oh, it looks like they also need, there's an optional quantifier in here, right? Whether it's one or all. So I'm going to put in here quantifier, right? Looks like I missed that. Empty optionals of a type. We look up a member in an object. We call and callee with arguments. We convert an expression to a type. An array literal has members. A dictionary literal has bindings. Each binding has a key and a value. An optional type is optional over base type, like int question mark. The optional integer type is optional int, so the base type would be int. For the promise type, again, int promise, bool promise, string promise, array of int, array of string, array of bool, or array of dictionary optionals, dictionaries with key types and value types. And so far, so good, all the way down to trying to deal with these things down here, like identifiers. Now, if I had an identifier, for right now, I think that if I ever had like the identifier X show up somewhere in my abstract syntax tree, I'm just going to store whatever the name of the identifier is. So if I ever encounter an identifier, I'm only interested, say, in its lexeme. Now, what about things like integer literals or float literals or string literals? Integer, float, string literals. Well, these things I'm just going to go with a plain old literal. So in order not to make too many classes, I mean, I could make an integer literal, Boolean literal, float literal. Yeah, in fact, I should probably do with Boolean literals too, which will handle that pretty soon. The integers, Boolean, strings, and floats, I'm just going to store in a literal object and then store their type with it. Now, if I ever have like an operator, a plus, a minus, times, that kind of stuff there, I might store that in an abstract syntax tree node as well. And I'm going to store that in a symbol node so that we can just store things like, operators and things like that. And now that I have all these core classes, let's make sure nothing broke. Okay, it's still working. Now that I have these, I can start taking these things and put them in the abstract syntax tree generator, okay? And it's going to work like this. This is going to be a recursive walk down the concrete syntax tree. Whenever I see a program, whenever I'm parsing a program, then what would I like to do if I'm parsing a program? I want to build a node for the or the program. In other words, a program has a body. So what I want to return is a program node. And that program node is going to contain in it its body. But I want to produce the abstract syntax tree for the body. So when I generate the abstract syntax tree for a program, it's going to be a program object with a body inside. When I generate code for a print statement, not generate code, sorry, when I build an abstract syntax tree node for print statement, it's going to be a print statement object, right? And remember, print statement objects right here, they just contain an argument. And that argument is going to be done by recursively going through and processing the expressions abstract syntax tree, which I misspelled. Okay. Now, for a variable declaration, what do we need to do here? Well, I'm going to return the core variable declaration. And that variable declaration is going to need an identifier, a type, and an initializer. So it's going to be the identifiers, abstract syntax tree. Now the types, here's where it gets kind of interesting. Remember that in the grammar, the type constraint in a variable declaration is optional. So what Ohm is sending us here is not an actual type object, but an array of type concrete syntax tree nodes, which may be empty or not empty, right? So I'd like to go through and process each one of these, but there might be 0, 1. Now, if there is 1, I would love to take the one and only one argument. It would be their position 0, but what if it's empty? Okay, if it's empty, the 0 part doesn't exist. Okay, so we can just say, all right, well, you know, if it's not there, I guess my type is null. This is one nice way to get a null in there. You know, you could also try to do something like that. That would give you undefined though, and I think we want null to say that it's actually not there. And then for my initializer over here, we'll go with the initializer abstract syntax tree like so. Okay, let's do a couple more. For assignments, we're going to return a new assignment object. And there's two things there. There's the target, AST, and then there's the source, AST. So far, so good. This one's pretty simple. Return a new while statement node, and this has a test.ast and a body.ast. Okay. Breaks are just break statements. Return new, whoa, that's not inside of here. Return new or break statement. And it's simply a matter of like running through what we have to run through. Okay. Do we get everything in here? I feel like I'm missing something. I feel like I'm missing function declarations. Yeah, after a break statement, there should be a function declaration. Okay, so yeah, I totally forgot that. Statement, function declaration. What do function declarations have in there again? There was, let's see, there was the keyword function. There was the identifier, parameters, colon, and then the return type, and then the body. Okay, return new core dot function declaration, and then ID params, return type, and body. Need a comma. Okay. Try statement. Okay, try statement's going to be, you know, sort of as expected right here. It'll look something like that. And you try statement with ASTs on everything. The if statement, I can just paste in here. You know what this is going to be. An if statement with a test, a consequent, and an alternate. Now, what about params? Okay, now params is where things get a little bit interesting because over here, I'm going to open the small.ohm on this side. And sure wraps over here a lot. Let's look at params. Now, params uses list of. So when I'm processing param, when I got to deal with params, I have to deal with that somehow. Like I have the word params over here, but this is list of. To handle list of in ohm, you would say params, like you thought, but then instead of saying params.ast, you can't do that because params is a list of, and we don't know like how to process list of. So if you are using list of or non-empty list of in your own grammar, you want to process it with as iteration on it. That's what you need to say. This makes params look like it was not a list of, but rather had all the parameters in place. Okay. So this is actually good for us to return, and this will work. This will work fine. For param, we're just going to put in the AST of the ID and type directly. No surprise there. Args, now args is another one of those things that has a list of. So because that has a list of, you want to take all your expressions and you want to do an as iteration on them. So take expressions, do as iteration before you do .ast. Okay. If we see a block, now we don't have a block AST object, so we're just going to go ahead and return statements.ast. Now, you might be wondering here, and rightly so, that, okay, if I have a list of, like I said before, list of here, I have to do as iteration. As iteration would be just like I had a star or a plus on something. It's like I had this sequence. But then you might wonder, wait a second. Okay, even if I do expressions that as iteration, it would be like in the case of block where I had statement star. What is this statements? This is an array of statements. These are not individual nodes, individual concrete syntax tree nodes. This is an array of nodes. So how do we tell ohm that we need to process all of the things? How do we tell ohm to process everything in the array? Well, in ohm, there's a special method on the semantics object called iter, just like underscore terminal is special. But with iter, you can give it a series of zero more concrete syntax tree nodes, and you can collect them into an array like so. So we say, here's all of the nodes, and then map over each child node and call the AST operation on it. This is what allows you to say things like statements.ast. This is how they would work. Now, that I think covers all of the kind of important things. So all the stuff we haven't done yet, from unwrap all the way down to, oh, we'll just go all the way down to the end. Yeah, from unwrap all the way down to the end. I'm going to just plop down the actual pre-built code here. And we can take a look at what's actually happening here. So for my unwrap, I just returned a binary expression for the unwrap. Unary expressions are here. The await was an await expression with timeouts. And now you notice that the quantifiers over here were possibly missing. They were possibly there, possibly not there. So I'm sorry, there might be zero quantifiers, there might be one quantifier. Here are all the different binary expressions here's a call, here's type conversion, here's parens, here's array literals, dictionary literals. I just do a mapping from what you see in the syntax to the kind of abstract syntax tree that you want to produce. And now an abstract syntax tree for hello small will turn out to give us an error. And it says here that print statement cannot be invoked without new. It's probably good that we have errors over here. Return a new program, new, because I was not thinking about JavaScript until down here. Let's try print statement again. And you can see now we're printing out an abstract syntax tree version of our program. Now, when Node prints out some objects, you can see that the printout doesn't go too deep. If I wanted to go a little bit deeper down there, I could go back into small and say, instead of printing out ast.match, we could print out util.inspect ast.match with a depth of null. And that would go deep for inspect, like so. So let's import util from util. This is a nice thing to know about. And then if I run it, it shows you, my program has a body with one statement, a print statement. The literal is a string with lexeme hello in it. And if I wanted to make my little program, what was that called? Hello. After saying print hello, I mean, if I wanted to make an assignment, x equals 5 times 2 plus 7 divided by 3. Okay. I could take a look at what this is now. Now my program is a body with a print statement, and then the assignment has a target of x, but then you can see here a rather complicated expression here. There's a plus with 5 times 2 on the right and 7 divided by 3 on the right. Sorry, this was the left. 5 times 2 on the left, 7 divided by 3 on the right. So if you want to take an arbitrarily long program and drop it in there, it will print out nicely. But now, we forgot our tests. So let's create a little file here, ast.test.js. And oh boy, how do we do a test here? I mean, I suppose what we should do is, well, let's begin with the describe, right? Describe the AST generator. What does the abstract generator do? Well, we want to assert that it prints out the things we expect it to. But this could take a long time, and the video is already getting long. So what I'm going to do is just shorten this down and say, let's just see that it actually produces an abstract syntax tree, just to make sure that something works, right? And the way I'm going to assert that is I'm just going to console.log the util.inspect of the AST of the parse of the source code. And what am I going to do for source code? Well, let's put some source up here. Call it source code, and I'll make a little program, and I'll start out by saying something like, well, let's print. Let's see if we can get some identifiers and some things in here like that. True or false. 73.2, and put in a variable declaration just for now. And then when I run this test, I want to make sure that we can first, well, I'm using util, I'm using parse, I'm using AST, and I wish that, I wish that VS Code would know this, but unfortunately it doesn't seem to. Import util from util. And let me bring in parse and import. And let's just run the test, npm test. ST generator does not produce an AST. Something failed over there. It says cannot apply semantics, match failed at position 22. Apparently there's something wrong over here. Oh, P1, I don't know, and true, let's say. Oh, it all passed. Okay, great. Actually, it passed and it produced a program of some sort over here, which is fine. But what I'm interested right now is making sure that we're actually getting good test coverage. You can see right here that a lot of lines are not covered. It says, for example, in core.js, we have not covered lines 152 and 153 inside of core. And 152, 153 are a dictionary. So this is telling me that in my test, I don't have any dictionary examples. So maybe, what's a good operator? I'll just use plus. Let's put in some dictionaries like x sub 2, y sub 5 is a dictionary. And I know I'm probably also going to need some array literals like 1, 2, 3. So currently I have 75% test coverage on that. Since I added those lines in here, it should be a little bit better. Yeah, I went up to 78. Oh, I still don't have 152 and 153 covered in core. That was a little surprising. Oh, sorry. This is dictionary type, not dictionary literal. How silly. Okay, let's put in some types then. Let's make a variable z have type string colon anything. Well, I'll make it optional for good measure. And then, yeah, it's, I don't know, it's 9. And then let's make a function called f, and let's see if we get some more types in here. An array of Booleans to make sure that works. And so that gives us optionals. X is a type Boolean. I don't know if there's any other types we need. Should return a string. We need a while loop in there. While false, do nothing. If true, do this, else do that. Okay, what's our thing? 75.44. See what we get now. 84.3. Okay, so let's get 140 and 141 in core. What are we missing over here? We're missing promise types. Okay, getting in a promise type shouldn't be too hard. I'll just slap a promise on this. And while we're at it, might as well do a try statement. Try print 1. No, it's trying to wait. Await 50 milliseconds to do something. Wait 50 milliseconds to call f of x. And if there's a timeout, we'll print 1. Otherwise, we'll catch a string and do something. Are we missing any statements yet? I guess we'll find out. Okay. Anyway, what I'm doing is I'm just walking through and I'm finding the uncovered lines. Oh, there was an error there. ST generator cannot apply semantics. Position 214. I have no idea what position 214 is. Oh, I'm sure I need one of these things here. It helps to. Oh, you know what I need? I need breaks. I need breaks and returns. Yeah, it's always better to like write stuff out so you can see a little bit better. Because the try has a timeout with a print. And then there's a catch. See if that's any better. Still got a problem. Position 262. See that? The error messages aren't too hot, are they? Also 232. Oh my God, this could be anything. What's at line 262? Or sorry, position 262. Well, if I commented out this if, oh, crazy, huh? Okay. Anyway, here's what I would say. It takes some time to get everything in your language. I don't really know what position 262 is. It's hard. It's definitely hard to find. Maybe I need a statement in here. Let's see if that's the case. Again, 262. Well, you know what we could do, and my tests are not very nice, but here's a nice thing you could do while you're debugging. While you're debugging, you can just drop this thing in here to bad. Plop the code that's failing into bad.small, and then just run node.small. Run small.js examples bad.small. It says right here, there's a problem with the weight. Oh, because a weight is actually not a statement. That's all it was. I don't even know my own language. Jesus. Okay, so why don't we just print that? And then we can npm test. And now we're way up to 91% test coverage, but there is an error. So you scroll up to find what the error is. It says there's a problem with return, missing semantic action for statement return. All right. So how am I missing statement return? That's a bit of a bummer. It's probably that I just forgot to put it in. Statement return as return and an expression. Return new core dot return statement. Expression.ast. Remember the comma. And, ooh. Now there's return has the wrong arity. Return has a semicolon in it that we forgot to put in. Bam, everything is passing and coverage is like way up here to 96.43. Through core line 110 and then lines 92 to 93. So let's do 110 and 92 in core. See what we're missing. And we're missing a type conversion. And we're missing an empty optional. Type conversion and an empty optional. So print one as a string and an empty optional. We'll say f of x divided by no int. And just lines 26 is uncovered in core. We don't have an assignment statement. Yeah, right. Out of all the things to forget, I had to forget an assignment statement. So there, now I'm assigning. Okay. And looks like AST 88, 72, and 96. 88, 72, and 96 in AST. 88, we're looking for conjunct. Okay, so I don't have any relational operators. On line 72, I don't have any unary operators. So let's put those in the test. We'll say, I don't know, weight -50. And I need a relational operator. So maybe 2 is less than 10. And just line 69 in AST is uncovered. We're almost there. I don't have any unwrapped tests. So I'm just going to throw in a, that'll look funny there, right? How about 2 ? X? That's the unwrap operator. And if I do that, boom, 100% test coverage. All right, now, okay, now obviously this test wasn't all that great. What I wanted to do with this test was just make sure that everything I put into AST.js didn't break anything. I didn't miss anything. You saw I forgot the return statement earlier. So this is a nice way to make sure that everything gets handled. Obviously, a real test would be more involved, and I'll leave that for you to play around with. But okay, I think until next time, we actually have a language that's been designed, so to speak. It's now ready for semantic analysis because we have an abstract syntax regenerated. I'll do semantic analysis in the next one. Until then, bye.